Hello, in this video we're going to cover 2.4, chapter 2.4 about continuity. But before we do continuity, I'd like to do an example on 2.3 because when I left off with chapter 2.3 part 2, I didn't have time to do an example. So let's just do an example for 2.3 before we start 2.4. So it goes like this. We know earlier that we have limit x or theta approach 0, sine x over x would equal to 1. So this is something that we have established with a proof using the unit circle. So if I am to do limit x approaches 0 sine 6x over x, can I do it? Can I just move the 6 out? We were told that we're not supposed, right? Because it's a function. So can I do it? How am I supposed to do? So this kind of function, this kind of question are pretty common. So the way we do it would be we know that if these two agree and x approaches 0, then it's equal to 1. But inside I have a 6x, outside I don't have a 6x, so it is very easy to do is to make it 6x and then times 6, because 6 and 6 will cancel. So actually I'm just doing a common equivalent fraction. So but then I noticed that when x approaches 0, 6x should also approach 0, right? So I'll write 6x approach 0. So all these are the same. 6x, 6x, 6x. You can replace it with u, right? U approach 0, sine u over u. All of a sudden, this part become 1 because of the limit that we established. And then we have a 6 outside that we use for equivalent fraction. So that's equal to 6. So you don't need to use like sum and product rule, double angle, those things. Just change the parameter. And then this one we'll do it in class. So let's go back to 2.4, which is continuity. Why do we do continuity? Continuity is used to it's used. There's a few things for the limit chapter. We use it to prove the composite rule. That means if I have a composite function, I can move the limit inside of the composite when I do limit. And it helps us to all of a sudden do like, oh, if I have a limit of sine x squared plus 2, can I actually do the limit? Because I know sine x, I know how to do that, but I don't know how to do sine x squared plus 2. So this is a composite function of outside is sine, inside x squared plus 2. So it helps us to deal with that. And later on, it also helps us to establish a lot of important theorem in calculus based on continuity. So what is the intuitive concept of continuity is we say a function is continuous if we grab it, we can grab it without lifting the pencil. So it's like all the way very smooth, very smooth. We don't even lift the pencil. If we have to lift the pencil, that must be because of something like that. That would be must be a brick or be a jump, right? So we have to lift our pencil. So what are the situation that there is discontinuous would be, oh, suddenly there is a hole, so we have to lift our pencil, or suddenly there's a jump, right? The function just break up like that, or the function go to infinity together, and then you do have to lift your pencil, or they go to positive infinity or negative infinity. So these are the cases where limit does not exist. Well, the last three cases, limit does not exist. This one, limit does exist, right? But this is still not continuous. So, so how do we formally collect all these together to say that these are not continuous? And if they are not, none of this case, then they are continuous. So what happens is you can look at the argument. So first of all, we say if there's no breaks, so all of the at x equal to a must be defined. So this would rule this out, right? And then for it to trace continuously, the two side limit must exist. So they must be smooth and they must be exist. So it has to be like continuously and then the solid and then like this. And also there should not be any jump, or does not go to infinity. So to avoid all this, we have to have the limit equal to f of a. So you can see that if the limit exists so that I don't have to jump my pencil, then this limit must be f of a and it has to be defined. So the definition of continuity would be like this. F of a has to be defined if at a it's continuous and the limit at x as x approaches a on the both sides would exist. It eliminates the jump situation. And then the limit is actually f of a. Okay, if any one of these is not satisfied, then f of x is discontinuous. I'm going to say it again. For x equal to a to be continuous for f of x, all these has to be defined. The limit has to have exist equal to one number on both sides, and f of a must be defined, and f of a must be the limit. Meaning when you are on the two sides meet here, this is actually f of a, right? So this would guarantee that it is continuous. It's very smooth. So to check the continuity of a function at a particular point a, so first of all, check if you can do f of a, if it is in the domain. Then you check you actually find the limit, and then you check that these two are the same. Okay, so let's check. Is x minus 1, x minus 3 continuous at x equal to 3? We know that if we put in x equal to 3, we have a divide by 0. So it is not in the domain, right? It's not in the domain. So x equal to 3 is not defined, right? It is not in the domain. So it must not be continuous. Not continuous. So x equal to 3 is not continuous at f of x, for f of x. What about example 2 is if f of x continues at x equal to 1, we can plug in x equal to 1 into the denominator. So 1 minus 4 plus 3. Oh, that's equal to 0, so it's undefined again, right? So undefined, not continuous, because it's not even in the domain. Now, for this particular case, actually, you can find the limit. Why? When you do limit x approaches 1 at x equal to 1, you have the top factor as x minus 1, x plus 1. The bottom can be factored as x minus 1, x minus 3, right? X minus 1, x minus 3, because you can say two number, -1, -3, when they add, they're -4. When they multiply, they're 3. So x minus 1, x minus 3. So x minus 1 cancel. The limit actually exists, but it is undefined. So this is the case when you have a hole. So it's still not continuous. So not continuous because it is not defined. What about this? This would be example 3. I have a piecewise function. To tell if it's continuous, I suspect that maybe it is at the boundary point, it may be not continuous, right? Because these are polynomial function. They are continuous in their own place. If you plug in x equal to 1, it exists, and the limit is also equal to side direct substitution. But at the boundary, we are not sure. So we'll do the boundary. So we'll say f of 1 exists first, because that's equal to this. It's equal to 2 times 1 plus 5, right? And that's equal to 7. So let's do limit. X approaches 1 plus. That means on the positive side, so that would be this side, 7, right? But limit x approaches 1 minus on the negative side would be -1. Oh, -1. No, it is actually -1 square, which is 1, plus 8. So -1 square is actually -1. That's 7. So limit agree. So limit x approaches 1, f of x actually equal to 7. And they are the same as f of x. So continuous. They agree. Okay, they agree. So you say that you have to evaluate, and then you have to find the limit. To find the limit of a piecewise function, you find both sides, and they agree, then it's continuous. Okay, the three conditions. Condition 1, condition 2, and condition 3 that they agree. Okay. The next things we want to talk about is types of discontinuity. So when things are not continuous, then they must be one of these types. So let me blow it up a little bit. So they must be that there is a jump or a hole. There must be a jump or a hole or going to infinity. So we give them name. We call them, if there's a hole here, there actually the limit exists. So you see, if you can fill this hole, then it would work. So we call them removable discontinuity. That means there's a hole. Okay, it could be removable. A jump discontinuity means that it breaks up. There's no way you can make it connect. And then there is infinite in discontinuity. Okay, so we can distinguish them. So now for the situation of the whole versus the infinite discontinuity, it happens a lot in rational functions. So in rational functions, if you have the denominator equal to 0, but you can cancel it, limit exists, but f of x is not defined, that is a removable discontinuity. So let's look at this. We have x squared minus 4 over x minus 2. F of 2 is undefined, right? Not defined. Not in the domain. But if I look at the function x plus 2, I factor the top, and x minus 2, this can be cancelled so that the limit exists. If I plug in 2, my limit exists. Limit exists means they agree on from the both sides. It's just that here in the middle they don't exist. It's not defined. So this types of discontinuity is the removable, right? Removable. The limit exists. That means they go in the same place, but then they don't go to infinity. Then it's a removable discontinuity. So what about this one? This one, when I plug in, so or actually you can define, you can look at it as 0 over 0, but then it is not defined like that. When you plug in, it is not 0 over 0, it's 1 over 0, right? It's k over 0 case. So in this case, what is the limit? So f of negative 1 is not defined because the denominator will be 0. And then when you do limit, so that's why you need to do limit. X approaches negative 1, you have a 1 over 0. So you split them up as x plus 2 times 1 over x plus 1. This would go to positive, negative, infinity, right? A constant, we will plug it in, is 1 times positive infinity, negative infinity is still infinity. So it's go to positive and negative infinity. So we can say it is infinite, it is continuity. It's discontinuous because of infinity, not because of removable. So limit allow us to distinguish whether the types of discontinuity. Okay. So what about this function? It's a piecewise function at x equal to 1. Is it continuous or not continuous? And if it is the case, what is the type? So let's try. So the only case this could have would be if they jump or not, right? So it's just a 1 plus the greater number. One greater number will be put in here. 2 times 1 plus 5 equal to 7. But if we do the left-hand side, 1 minus, we use this function. 1 negative 1 squared plus 3 would equal to 2, right? So 1 squared is negative 1 plus 3 is 2. They don't agree. So this is the case when we have from the right hand side is 7. solid, and the left hand side is 2. Okay, so this is a jump